ArGue, attributes-guided prompt tuning for vision language models. Imagine that we want to adapt pre-trained vision language models a special clip on the biased dataset such as the colors, the meanest, where each digit is actually aligned with a specific color such as green for 0 and purple for 2. The adaptation of vision language models may face with the problem of excessive attention on the color background, which is the bias, instead of the digital itself, as shown in the picture, where the white blanket represented the clip's attention. But the truly problem is how to know exactly the class, which is the digit in this case. By solving this issue, we can prove novel class prediction and out-of-distribution generalization. In solving this problem, we provide an intuitive solution. In human eyes, in distinguishing an image's category, we will decompose the category into multiple primitive attributes, such as the long tail and the wet hand and the gray body for a category of cat. So if we can let the clip can learn the intrinsic attributes in a category, it can solve the problems mentioned above. Specifically giving a set of attributes associated with a certain class, instead of directly providing the class label, we also want to train a model to produce high similarity to these attributes. Naturally, we believe that a model providing high confidence on the correct attributes grabs the essence of the class. It can bring benefits. Firstly, it naturally elevates the bias in our image. Secondly, the low-level semantic tend to be generalized. But also it can bring the problems. Are all the attributes really what we want? So we provide the attribute sampling. And the pre-trained model still incurs bias, so we provided the negative prompting for this problem. Following other works like dclip, we prompt the large language model to generate the class-wise attributes. But it brings the question, is every attribute generated by large language models useful? Here we'll provide two counterexamples for sketches. It sometimes will produce the long visual attributes like sweet taste or edible, and sometimes it will produce the semantically unrelated visual attributes like red and yellow in color. And also we empirically do an attribute study to train on every attribute iteratively on multiple datasets, such as Euro, SAT, or Food 101. And we can notice, or we can make a conclusion, is that some attributes are much better than others. And combining useful attributes further enhance the results as shown in the table. In order to find the most useful or the most representative attributes, we propose the attribute sampling. It contains two considerations. The firstly is that the selected attributes should be representative and non-redundant. Secondly, the selected attributes should be semantically related to the images. Here, the attribute sampling contains three steps to find these kind of selected attributes. Firstly, it clusters the attributes within the clip space, and then it will rank the attributes per cluster based on their similarity to images. And third, selected the attributes with the highest similarity per clusters. And here we also provided two example classes from the ImageNet and ImageNet Sketch for the attribute sampling procedure. Additionally, in order to making sure that the adaptation of vision language models can getting rid of the effect by the background, we provide the strategy called negative prompting. It comes from the intuition that different prompts that can activate the distinct pixel areas. For example, if you are giving a cat images and giving a standard prompt such as a photo of a cat, then the clip attention will more focusing on the cat itself. But if your prompt is actually the negative prompt, which is the background of a cat, then it will more focusing on the background. Here, motivated by this, we provide a new strategy to enforce the model to ignore such negative prompts, which will potentially getting rid of the effect by the spurious correlation. Here we provide a simple method overview of the ArGue. So in stage A, giving a class name bobolink, it will firstly feed into the large language model to generate the attributes candidate through the different templates. And then the attributes candidates along with the bobolink images will be encoded into the clip space with the text encoders and the image encoders, which are all frozen. And then the attributes sampling procedure will be proceed to generate the sampled attributes of the bobolink. In the stage C, where the most of the training happens here, the sampled attributes and the bubbling images will be used to load the soft prompts, which are all the loadable tokens. And then it contains three losses. First is actually the losses for entropy loss, and secondly is the regularization loss, and the third is actually the negative prompting loss. The details can be shown in our papers. Please check there. And here we also provide several result visualizations where the stage A is actually the class label and with the original images, such as British short hair and the red rabbit. And in the B, we are demonstrating the comparison with the baseline methods, where the standard prompt is actually a photo of British short hair and a photo of white rabbits. Our method can be many presented in the ArGue N. We can say that there is a little attention on the background, and it mainly focusing on the object itself. In the attribute C, we also provide several attribute visualizations. And in the stage D, we provide the negative prompting's attention, which is actually the prompt with the background of a British short hair and the background of the red rabbit. Thanks for your listening, and here's all the contents that we want to present for our method ArGue, and thank you so much again.